Well, hello everybody, Dave here, and we're going to start a series of lessons on how we can describe relationships with plots and calculations after the fact. We're going to deal with this idea of scatterplots, which is something that hopefully you've dealt with in previous courses. But instead of just playing around with the idea of statistical analysis of scatterplots, we're going to go on it head on, dealing with least squared regression lines, correlation, and the idea of the coefficient of determination as a means for coming up with meaningful conclusions and hopefully a relationship and even possibly a cause and effect scenario for a given data set. So the first thing we need to do is just redefine some things just to make sure we're all on the same page. And when we talk about variables now, we don't want to talk about x and y and things like that. We want to talk about horizontal and vertical axes and explanatory and response variables. So when we talk about the response variable, it sounds like what it actually is. The idea that we've controlled something and there was a response from it, and that's what we've measured. And so the outcome of the study, the measured outcome, is really what the response variable represents. When it comes to the explanatory variable, we're talking about the thing that we are controlling that we are hoping is causing, or at least that leads to some sort of response in the response variable. And so this idea of cause and effect is something that becomes very important when we discuss scatter plots and the various quantities calculated from it. And our ultimate goal when we have variables is to try and establish a relationship between them such that the one has caused the other. Now, this doesn't happen from just the mathematics alone, but it does begin to give us a relationship that hopefully leads to that, given more information about the study itself. But in general, correlation, or the relationship between two variables, does not imply causation, that there has to be more situations involved there in terms of the experimental design of the study itself. So a scatter plot is what we're going to do to try and establish some sort of relationship between these two variables. And it's important first and foremost to know which variable we graph on which axis. And this is something that, depending upon the study, is going to be a little tricky to understand. But generally speaking, when we identify what the explanatory variable is, that's the one that we're going to put on the horizontal axis, or from classic sense, the x-axis. And then the response variable, which is the one that we're hoping we establish a relationship between it and the explanatory variable, that's the one that's going to be on the vertical axis, or the y-axis. Because again, we are trying to potentially suggest that there's a relationship to maybe further determine that there is an actual cause and effect relationship between the two. But if you don't graph them in the correct axes, then the graph that you get is going to give you quantities. It's going to give you slopes and correlations and things like this, but those values are going to be relative to a plot that doesn't actually represent an explanatory response relationship type scenario. So please make sure that when you're reading these problems, you make sure that you identify which one is which appropriately. Now, when we're describing scatter plots, you'll remember from chapter 1 we started playing around with this idea of SOCs as a means for describing distributions. But in this case, we're dealing with a scatter plot of two quantitative variables, which means we have to change the way in which we describe these particular patterns. And for this, we go to FODs. And FODs stands for form, outliers, direction, and strength. And these are going to be the four quantities that you're going to want to look for and describe when you're asked to describe a scatter plot. So when we talk about form, is it linear or is it curved? When we're talking about strength, is it strong? Is it weak? Is it moderate? Outliers are going to be based upon its distance away from the overall distribution, and not necessarily from a distance perspective, but from an overall deviation away from the pattern itself. And finally, direction, we're going to relate to our understanding of slopes of lines as being either a positive or negative direction. And that's just going to be based on a line that looks like a positive slope and a negative slope. So let's take a look at an example right here. We have a distribution of mean math scores as a function of the percent of the people that took the SATs. And you can see here that we have an overall shape to this scatter plot. And from it, we can begin to understand the relationships. Now, as of right now, we don't have any curve fitting or line fitting that we can do. So we simply have to look at the points and decide for ourselves, what do we see? Well, the first thing we see is a strength. And we can see that the points are generally clumped together and moving from the upper left corner kind of down to the bottom right corner. But you can see that this band of points is generally close together, which indicates a moderately strong distribution. If these points were closer together, you might even go to say that it's a strong distribution. And if these points were spread out a little more, you might say that it's not so moderate, it's more of a weak strength. When it comes to the direction, you'll notice that as it goes from the top left down to the bottom right, that's moving in somewhat of a negatively sloped direction. Again, if you imagine yourself with a linear relationship on there, then it would have a negative slope to it. So for that, I'm going to call that a negative direction. And because I look at this and I don't see a line, I actually see a curve. The form for me is going to be a curved distribution. It's not going to be a linear distribution. When it comes to the calculations we do later on, we're always going to be dealing with linear cases, but certainly early on in your identification of distributions and their FODS properties, don't be afraid to say that it's actually curved. But what you don't want to do is say what kind of curve it is, because a lot of students tend to point to curves that they understand. Oh, it's a square root form or it's a quadratic form. We don't know anything about that at this point. All we see is that it's not linear and it's certainly curved in some format. So this sentence here of there is a moderately strong negative curved relationship between the percent of students in a state who take the SAT and the mean SAT math score, that right there is the complete version of FODS outside of the outliers discussion. And so unlike SOX, where we listed things off into 4 points and we just made sure we hit all 4 points, a singular sentence can essentially take care of all the description. The last thing we need, though, is the describer of the outliers. And in this case, we're looking for points that are off the actual direction and the shape of this distribution. And so I can see 2 points. There's one at 20, 500 and one at about 87, maybe 460. Those points deviate vertically a lot more from the overall form of this distribution than any of the other points. And so because of that, I consider those to be potential outliers. We can't deal with an IQR test or anything in this case. We just have to go by the visual alone. But one of the things that comes from this now is the complete description of FODS, and we can refer to this as either a positive association or a negative association, again, just based simply on this direction of being negatively sloped or positively sloped. So if we have a different distribution like the one we see here, let's say we're talking about wins as a relationship to points per game, we can see the direction in this case. Certainly the points are moving from the bottom left of this graph up towards the top right. Well, that kind of looks like a positively sloped line. So we would say that the direction is certainly a positive direction, which means we believe there to be a positive association. When we talk about the form, this one looks far more linear, so we'd refer to it as linear. And when it comes to the strength, you can see that within that description of a linear direction, those points are generally close together towards that direction, so we would indicate this to be a strong relationship. So again, when we go back to that singular sentence, we would be talking about a strong, positive, linear association between the two variables. When it comes to outliers, there's no points that are vertically far away from this overall direction of this distribution, so I would not indicate that there are any outliers present in this case. Again, there's no calculation to be able to do this, but it's certainly a pretty easy thing to see when you have an outlier. Now, it would be nice to have a quantity that allows us to identify these things a little more directly, and for that we can actually come to calculate the correlation coefficient. Now, there's a shift in discussion that we're going to do here. We're going to focus now on distributions that we've deemed to be linear associations. When you have curved associations, there are different quantities that you can calculate for it. But the correlation coefficient that we're going to be describing here is going to be focused more on linear associations that from the visual appearance, we have determined that, yep, I think that that could be linear. So the correlation itself now is going to be a quantity that we can use to describe the direction and strength of a linear relationship between two variables. And this number is going to be a value between -1 and 1, where the negative sign represents a negative association and the positive sign represents a positive association. And based upon the actual magnitude of the R value, we're going to know whether it's a strong relationship or a weak relationship or something in between. And the basic idea here is that a number near 0 indicates a weak relationship, and a number near 1, whether it be negative or positive, represents a strong relationship. The extreme values of -1 and 1 show a truly perfect linear relationship. Now notice again, I am not saying that I have proven that something is linear. I am saying that from my visual I have deemed it to be a linear association, and this correlation coefficient is going to allow me to make further discussion about how strong a relationship it is. Now, if we take a look at 6 different scatter plots, you can begin to see what correlation looks like relative to the visual cues of a graph itself. You can see in the bottom right there that you have a scatter plot with the values essentially along the same line, and we end up with a correlation of -0.99. That negative should make sense again because that linear association sure looks like a negatively sloped line. As you move around these scatter plots, though, you can see how even with scatter plots that look like they're fairly spread out, they still have at least a moderately strong correlation. You can see the one in the bottom left with a correlation of -0.7. That still is considered to be at least moderately strong when we're talking about strength. As you come to the top, though, you can see that correlation becomes exceedingly challenging to identify by eye. When you look at the top middle value of -0.3, it's really hard to discern by eye that this would be a negative association first and foremost, and from there to what strength level we're talking about. We would know that it's fairly weak, but the actual magnitude of the R value would be a challenge for us to identify by eye alone. You can see the correlation of the plot on the top left there is a correlation of 0, and the reason for that is you can't look at this plot and discern any which way. If you tried to fit a line to this particular distribution, what way would be considered the direction of this particular scatter plot? So when that's the case, we consider it to be a correlation of 0, i.e. there is no relationship between the two variables that are being plotted there. So correlation is exceptionally challenging to identify by eye. There are websites available online to prove this to you by giving you a variety of scatter plots that you try to indicate the exact correlation of it, and then you find out more often than not that you're either too weak or too strong. So we would rely on our technology to allow us to determine this a little more easily than it would be by eye alone. Now, to calculate the correlation, there is this big ugly equation that you see at the bottom here. And the important thing that you need to understand by this equation is if you take a look at the very last equation, it says that it's x minus x bar over s sub x times y minus y bar over s sub y. And essentially what we're doing is for every observation, we're taking the difference between the observed value and the average and dividing it by the standard deviation of that particular column's standard deviation. So we deal with the x values on their own, we deal with the y values on their own, and then the product of those differences divided by the standard deviations allows us to calculate what the correlation is. Now, if you have a data set of 50 points, 100 points, 600 points, then calculating this by hand would be exceptionally tedious and take a long time. So we're certainly going to need to rely on technology to do so. And within your TI calculators and your graphing calculators, when you go to plot a scatter plot and create a regression line to fit to your plot, one of the calculations that does come up is the correlation coefficient as well as the R squared value, which is the coefficient of determination. For those of you with TI calculators, you need to make sure that you go to your catalog and turn your diagnostics on. I always do this with my students at the very beginning of this chapter so that they know that it's on, but you certainly want to take a look at what it means to have diagnostics on because it'll actually show those calculations for you. Don't worry about this equation as far as being able to actually use it by hand, but certainly understand that we're taking these differences between the observed and the average of each of the variables and the values that we have. Now, there are some things about correlation that we have to be careful about. And the first thing about it is it doesn't know whether you've graphed your variables right or wrong. So if we flip-flop the axes and graph the explanatory variable where the response variable should be and vice versa, what you end up with is the exact same correlation. And if you look at the mechanics of how the correlation is calculated, i.e. the last equation, you can see why. because at the end of the day, it's still just doing the difference of the observed value minus the mean and dividing by the standard deviation of that sample. So it doesn't know whether you've graphed it right or wrong. So please don't think that correlation is going to make a distinction between the variables, and as a result, that means it's not going to change even if you've graphed it wrong. The second thing is that it does not change when we change the units of measurements, regardless of which variable we are changing. And again, this comes back to the understanding of the mechanics of the calculation itself. This is why I show that equation, so that you understand that these various things, when we change them or when we make mistakes, it doesn't actually affect the value of the correlation itself. And just for the record, the correlation itself also has no units, and that should make sense from the equation. When we had units on the top and units on the bottom, they would cancel each other out when you actually perform the correlation calculation. So these three important facts about R are something that can all be gleaned from the equation itself. There are some cautions that you have to think about anytime we talk about correlation. The first is that we are dealing with quantitative data only. When we get to chapter 11 and talk about the chi-squared distribution, we can actually play around with the categorical data and trying to find relationships between those. But for right now, all we can do is have a data set where we have two quantitative variables, and that's what we're going to plot on the scatter plot, and that's what we're going to use correlation for. We also can't use correlation to describe curved relationships. There are quantities that describe curved relationships, but that's beyond the scope of this course. So if you need more about that, you're going to have to go online and find it. Correlation is also very, very not resistant to outliers, and even 1 point in an entire distribution of points that appears to be linear, 1 point off of that distribution can have an adverse effect on the calculation of the R value, which is why a lot of people do the improper thing of just simply removing outlier points in a scatter plot. And if you can determine a logical reason why to remove it that isn't just I want my correlation to be better, i.e. there was a procedural error, or maybe there's an input error, or maybe there's a reason to justify why that data point does not represent what your study is, outside of that you have to leave it in. But you can see why people remove it in a little bit when we show an example of a point being removed. The final thing to recognize is that the correlation itself is not the complete summary. Remember that we're talking about FODs, and this one gives us the direction, and it tells us about the strength, but we also have to go through the rest of FODs and talk about form and talk about outliers. And so you can't just simply state that the correlation is a particular value and leave it at that. Make sure that FODs has the complete description of your particular distribution in the scatter plot. So let's go ahead and do an example here where we tie this all together. And we have here a table of the 2011 college football season with a bunch of teams that scored some points per game, and that resulted in some certain wins. And we'll go ahead and make a scatter plot of the relationship between the points per game and wins. We'll interpret the correlation value of 0.936 in context of the problem, and then determine what happens if we remove one of the lowest points on the scatter plot. So this is what the scatter plot would look like, and you can see right away that we've made the determination that the points per game were the explanatory variable. And that should make sense because it is the number of points you score per game that results in the wins, not the other way around. So in this case, the implication was that the response variable was the wins and the explanatory variable was the points per game. Now, just looking at this from a FODS perspective, we can see that it is linear. We can see that it is a positive association that is moving from the bottom left to the top right. We can see that there are no outliers present, and we can also tell that the strength is rather strong just based upon the fact that the points are generally clumped along this linear direction. With a R value of 0.936, we do know now that it is a strong relationship, and to interpret this value in context of the problem, the language that we use here is somewhat scripted. The correlation of 0.936 tells us there is a strong positive linear relationship between points per game and wins in the SEC. So that's an important thing to recognize because that's all that the correlation tells us. It doesn't tell us anything else that we talked about with FODs, but it does give us a lot of information that we can use to describe this overall distribution. If we now try to remove that point, which I've circled with a green circle, if we remove that point, what's going to happen is just looking at the points themselves, it's not going to be as linear or as tightly clustered. You can see that things start to spread out a bit. And that point on the bottom left there was really helping the overall direction of this linear association. And when we get into linear regressions, you're going to find out that that point there really helped the linear regression understand the direction that it was going. And so, although it seems like that point is right along line with the rest of the distribution, the problem with this one is if you remove it, it makes this overall scatter plot a little less formed. And so because of that, we would argue that the correlation is going to decrease. If you have the data set, you can very quickly remove it and calculate the correlation to find out that that's exactly the case. So 1 point removed can drastically change the correlation. How much so? This question isn't necessarily asking for. But what a lot of students do when they have the full data set is they prove to themselves that it adjusts it by making it lower or higher by actually going through the full process within their calculators of calculating the new correlation and relating it to the previous correlation. In this case, a simple visual cue was enough for me. So folks, that's it for the first lesson in this particular section. It's important that you get into your calculator and get used to making scatter plots. I know a lot of people have done scatter plots in the past, but using the tool that you're going to use throughout statistics is a vital important part of the learning process, so please get in there and work on it. Definitely play around with the data sets and understanding when you remove points how much that drastically affects the overall form and the directions of your relationships, and most of all, make sure that we're clear on the different language that we're using to describe these relationships and what the correlation tells us and what it doesn't. So best of luck to you, and we'll see you again.